Hello everybody. In the previous lectures, we generally concentrate on representing and modeling dynamical systems. We technically try to solve a system of equations of mechanical systems, try to find transfer functions, state representations for electromechanical systems with DC motor and other kind of components. Okay, from now on, we will technically move on to more analysis and controller design parts of the technical course. And instead of dealing with the mechanical or electromechanical systems, we will generally deal with transfer functions or mathematical models of some plants. Okay, so G of S is generally the plant transfer function, which is technically transfer function of the physical system. Okay, C of S is the controller that we design and implement. Okay, as you can see, this is a negative feedback loop. And H of S is generally stands for sensor or transducer dynamics, okay, which is technically part of the system, but mainly it's technically there's some sort of dynamical component between the measurement, which is here, and actual output of the system. Okay, that's great. And as you can see in this block diagram, we have three inputs: R, D, and N. R of S is the reference input or reference signal that we try to technically track in the closed-loop system. This is the most important input of the system, but it's not only important input that you need to technically take care in a control system design. Okay, there are some sort of unwanted inputs that we don't know exactly. Okay, so we may know sometimes, but these are technically input signals that we want to reject or eliminate in the closed-loop system. Okay, we don't want to reject R of S, we want to track R of S, but we want to reject D and N in a closed-loop system. This is one of the most important technical concepts in control system design. So some inputs that are desired, okay, and some inputs that they are not desired, and we want to try to reject in the closed system. Okay, so when trying to find the transfer function, we for a multi-input single output system, okay, what we do is we try to find transfer function one by one, from R to Y, from D to Y, from N to Y, and when doing it, we assume that the other inputs are equal to 0, such that, okay, D of S is equal to 0, N of S is equal to 0, and we know that transfer function from R to Y is very simple. It is a classical feedback loop. So T of R, let's write it here, T of R of S is equal to, okay, so the feed forward part, C of S times G of S, 1 plus multiplication of all of the components in this path, C, G, and H. Okay, so C of S, G of S, and H of S. That's great. This is the transfer function from, let's write it here, Y of S, R of S. Okay, from R to Y. Okay, that's great. So let's move on to the second input, and let's assume that N is equal to 0. Okay, R is equal to 0, but D is not equal to 0. Okay, so let's try to find transfer function. Okay, in this case, so what is the signal? We know that the signal is equal to D of S plus, okay, so if we go back here, there is a minus, go back here, this minus is important, so it is equal to Y of S, that's great, times H of S, C of S. Of course, we have minus 1, so this should be equal to minus, okay, this is this signal. If I multiply this signal with G of S, I obtain Y of S. Okay, it's very simple. Okay, so if I group it, as you can see, I'll do it now. D of S multiply with, okay, G of S, okay, that's simple, is equal to Y of S. Okay, that's great. Okay, so 1 plus, okay, Y of S. Okay, and here we have G, H, and S. Okay, that's great. G of S, H of S times C of S. Okay, that's great. So if I obtain Y, it's equal to G divided by this. Okay, so T D of S is equal to G of S. We have a different numerator. 1 plus C of S. Okay, G of S, H of S. That is super nice. Y of S divided by d of s. So what does it mean? As you can see, we changed the numerator, but we didn't change the denominator. Okay, so this is one of the important things, and you will see that we will have the same path when we find transfer function from n to d. Okay, so d is equal to 0. So, and finally, d is equal to 0, so we can ignore it, just move it here. R is equal to 0, it's the same, but n is not equal to 0 in this case. Okay, let's find the transfer function. Okay, so what is the signal? We know that it's equal to y of s minus n of s. Okay, so what is this signal? We know that this multiplied with h multiplied by minus, it's equal to n of s times h of s minus y of s times h of s. Okay, it's the signal. If I multiply this with c and g, I will obtain y again. It's equal to c of s. No, okay, it's not equal to. If I multiply this with c of s, g of s, I will obtain y of s. That's great, I think. So if I find the transfer function, this is n of s times, it's interesting, c of s, g of s, h of s. That's great. It's equal to y of s 1 plus, let's make it simple, c times h times g of s, of course. So let's write the transfer function. Okay, t n of s is equal to c of s, g of s, h of s divided by 1 plus c of s, g of s, h of s. That's super great. Y of s is divided by n of s. Okay, so these are two different disturbance signals. Okay, let's go back to the original topology and try to comment on the result. Okay, reference signal is signal that we want to track. Okay, that's nice, we know that. Okay, d of s is called process disturbance or process noise. N of s is called measurement disturbance or measurement noise. Okay, this is technically affecting the input of the plant, and this is technically affecting output of the plant. So physically and like structurally, there are different kind of unwanted inputs. Okay, so now we will do some sort of sensitivity like disturbance analysis, but it will be very rough. Okay, so it will be that's kind of a lousy way of technically analyzing these different kind of transfer functions, and we will try to come up with some ideas about what we can do about the controller such that we have a desired output. Okay, so let's first of all try to understand that. Okay, we want to track R. Okay, so we don't want to reject R. R is the reference signal and it has the same units of phi. If it's meters, it's meters. If it's angle, it's angle. And we technically want that, okay? So let's change the color. From the perspective of the reference tracking, we want that y of s is approximately equal to r of s, right? Okay, so when we talk about s, so what is approximately? It's kind of can be tricky. Okay, so it's generally easier to understand this equality when we talk about the frequency domain response or frequency response functions, and I will talk about later. But ideally, we want them to be exactly equal to each other, right? Okay, so if it's that, it's perfect tracking. Okay, I give input, I obtain the same output, which we cannot do, of course, in most of the dynamical systems. But this is the basic idea, right? Okay, if we take the inverse Laplace transform, okay, if we plot them, okay, if we compute y of t, if we compute r of t, we want them to be approximately equal to each other for each t. Okay, so this is the basic idea. So we want some sort of equality or like the approximation. But again, since we have s, it may be a little bit dumb, which is true. But we can still talk about this kind of rough analysis. Okay, good. So in that perspective, we want to reject d of s at the output. Okay, so we don't want to see any d, any like contamination of d at the output. So this is easier. So we technically want that td of s is equal to 0 and t1 of s equal to 0, Okay, so and this is equal to 1. Okay, so since we want to track R, okay, we want the perfect response, we want y of s to be approximate to R, which means that the transfer function should be equal to approximately equal to 1. Again, if we talk about in frequency domain response functions, which will be easier, but still we can talk about this kind of analysis. And in the other transfer functions, I want the transfer function to be equal to 0. Okay, now let's look at the topology. This is plant. Okay, once I design my plant, or when it's given to me, I cannot change it. Okay, I can make some changes, but they're general physical changes. It's major. H of S is the transducer dynamics. When you select your sensors, it is fixed. The thing that you can control in general in most of the systems is C. Okay, or basically the thing that is easier to control is C, not H, not G. G means that you need to change your physical system. H means that you need to change your sensors. C means that you need to change your code or controller, which may be easy or which may not, but it's in general, if we talk about relative perspective, it's easier to change than G and H. Now try to understand it, what we can do about C such that we can have a desired response. Okay, good. So we want this to be equal to approximately 1. Okay, so what we can do that, as you can see, so if C is very large, let's look at this. If C is very large, okay, it's very huge compared to G and H, okay. So if C of S, okay, C of S is very, very large, it's big, it's a high gain system, okay, from this perspective. In this case, this part will dominate the numerator behavior, and if we take the technical approximation of this, okay, so if it's large, we will see that TR of S will be approximately equal to C of S, okay, G of S, okay, this will be equal to C of S times G of S, H of S. In that respect, it will be equal to 1 over H of S. Okay, that's great. Okay, this we can do. So what is H? It is a transducer dynamics. Okay, so it's very nice that. So it says that there's a limitation. Okay, so we can make a perfect controller, but we are somewhat limited with H, which is true. Okay, first of all, it means that there shouldn't be any DC bias between Y and R, which is true, because if you have a DC bias, so if H of S is equal to like 1 or 2, it means that you're technically measuring the output wrong. Okay, and it also says that there shouldn't be like big phase lag in H of S, which also makes sense, because which means that you are measuring something that is in the past, which is kind of wrong. Okay, so once your H of S is approximately equal to 1, and this is the technically, if you are designer of a sensor, this is, you try to manage this in the frequency response function. You try to make it like that. It is approximately 1 across all spectrums, of course, if you eliminate the noise. Okay, that's great. So what we want is, from this perspective, okay, so if we have a high gain C, we technically manage T of S to be equal to approximately 1 over H of S. If our H of S is approximately equal to 1, it will be approximately equal to 1, which means that we have a good tracking response. Okay, from this perspective, what we know that for a good control system, for a good tracking performance, we need a high gain, okay, C of S, high gain feedback controller. We want an aggressive feedback controller. So this is the story. Okay, so what is high gain? Okay, it depends on your controller. Okay, it depends on your system performance. Okay, it can be just a constant, or it can be some sort of periodic controller. And definition of high gain can depend on S and can depend on the frequency response. Okay, but this is the idea. It should be large. Okay, now let's go to the disturbance. We want this to be equal to 0, but it's good that, as you can see, the C is in the denominator. It's not in the numerator. If I again adopt the high gain controller, this will be equal to 0, right? So we know that the large C of S is technically achieves that TD of S will be approximately equal to 0, which is a technically desired behavior from our perspective. That's great. Okay, so for a good performance in terms of disturbance rejection, we want a high gain C of S. This is truly great. Okay, so it means that a high gain controller satisfies good tracking performance, good disturbance process disturbance rejection performance. That's super great. Okay, we really like that. Okay, now let's go to the controller. Okay, so if I apply a high gain controller, okay, so T on of T, let's change the color again. T n of S, as you can see, since we have C, its high gain will be equal to 1. So what does it mean? I pass the noise or disturbance directly to the output. This is a super unwanted behavior. Okay, this is bad, right? So I have a noise or disturbance, I just pass it directly to the output. So it's not a good control policy, right? So instead, what I can do is I can use the fact that this is equal to 1. What I can use, I can make C as small as possible. It's very little, like C of S is approximately equal to 0, which means that I have a low gain controller, C of S. In that respect, I can achieve that T on of S is approximately 0, which means that I don't observe, or it's kind of negligible at the output. Okay, is it great? No. The problem is, okay, as you can see, for a good tracking performance, you need to adopt a high gain controller. For a good disturbance process disturbance rejection, you need to have a high gain controller. For a good measurement disturbance, measurement noise rejection, you need to have a low gain controller. Okay, this is called the fundamental limitation in a feedback control system. Okay, you cannot avoid it. It exists in any control system. It's one of the most simple control systems because it's kind of single output, okay, and single input in terms of the control action here. As you can see, even if you go to multi-input, multi-output systems, you need to deal some sort of this kind of limitation or this kind of trade-off where you need to technically choose a middle path between using a high gain and low gain controller. If you go high gain, you will be terrible in terms of like measurement noise rejection. If you go low gain, you will be terrible in terms of tracking and disturbance rejection. Okay, so what we can do, okay, and in order to answer this in a more deep fashion, we need to talk about the frequency response function and frequency response analysis. The good thing is, okay, by nature, okay, if you design your system nicely, okay, first of all, you try to eliminate these as much as possible, okay, because you are the designer of this. Okay, the electrical engineers are designer of this, and this is technically part of mechanical and or mechatronic system. Okay, so at the design phase, you need to be careful, and a good design generally satisfies a low D and low N of S at the beginning of your controller. Okay, once you make a good design, you still need to deal with some of the limitations. Okay, because if you make a high gain C of S, you can still amplify N of S at the output, which is a bad thing. But the good thing is, one more good thing is, okay, by nature, D of S, which is the like process noise or process disturbance, is generally affects system at low frequencies. Okay, this can be good or bad, but this is the basic idea. Low frequencies like the DC, like the couple of hertz. Of course, a couple of hertz depends on the system, but basically, if your bandwidth of the closed-loop system is F, it generally affects your system in the order of like F divided by 10 or something like. Of course, it depends on the system. Okay, so this disturbance is generally a low frequency behavior. Reference signal is also a low frequency behavior. We generally try to track like the step, ramp, or the signals that are like smooth and nice. They are not stochastic and noisy. It's technically stupid to track a stochastic or noisy high frequency reference signal. Reference signal is also generally, for majority of the system, a low frequency signal, and generally we try to feed this RFS into the system. And noise, okay. In sensor design, what you try to do is first you need to eliminate the bias and low frequency behavior at the design phase. Okay, so In that respect, you try to design your sensor system such that you eliminate all possible low frequency behavior and you are left with high frequency noise. Okay, and if you are high frequency noise, you can still filter them using filters, okay, other kind of things. But the idea is, if you try to manage this distinction at the design phase, okay, so let's change the color again. It means that, okay, so at low frequencies where RFS and DFS is dominated, you can make a design, a control system design, and at high frequencies, since these are technically negligible, you can adjust your design with respect to NFS. In that respect, what you do is, at low frequencies, you adjust your CF such that it's a high gain controller. At high frequencies, you adjust your gain such that it's a low gain controller. By doing this, okay, you can manage a system where you have a good tracking, process disturbance, and measurement noise disturbance rejection performance. Okay, so this is technically a rough way of analyzing disturbance rejection and reference tracking in control systems. When we once we learn new tools such as like the Nyquist, phase margin, and gain margin, it will be easier for us to address this topology in a more complicated fashion.